Hi everyone. In this video, I am going to tell you about Thevenin's theorem. Thevenin's theorem is basically used when you are interested only in a particular branch of a circuit and you don't care what rest of the circuit is. Before going through its statement, let me first tell you some of the basic terms that are used in its statement, that are what is a linear network, what are active elements, and what are passive elements. So first thing, what is a linear network? In simple words, we can say a network which is composed of only linear elements, that are resistor, inductor, and capacitor, is a linear network. But more precisely, a network is said to be linear if the parameter doesn't change with change in voltage or current. For example, for a resistor, the parameter is resistance, and if we change voltage across it, its resistance should not change. That is, if V is changed, then its should not change. And from VI characteristics of a resistor, we know that if voltage is changed across this resistor, then its resistance does not change. So this is a linear element. Similarly, in case of inductor, if voltage across inductor is changed, its inductance doesn't change. And similarly for a capacitor, if voltage across capacitor is changed, then its capacitance does not change. So RLC are linear elements. So any network which is composed of RLC is a linear network. But on the other hand, if we see a PN junction diode, then if V is changed, then its resistance changes. And we know this from its IV characteristics. That is, if V is changed, its resistance, that is inversely proportional to its slope, changes. So this is not a linear element. So Thevenin's theorem is applied only for linear networks, which is composed of R, L, and C. Now the second term is active elements. Active elements are those elements that supplies power in electrical circuit. That's why they are known as active elements, because they supply electrical energy to the circuit. And the third term is passive elements. Passive elements are those elements that consumes or stores energy. So all three elements R, L, and C are passive elements. Diode is also a passive element because it consumes energy. But diode is not a linear element. Now let's come to the formal statement of the Thevenin's theorem. It states that across a pair of terminals, any linear network containing active and passive elements can be replaced by an equivalent network containing a voltage source VTH, which is known as Thevenin's voltage, and a series resistance RTH, which is known as Thevenin's resistance. So to illustrate this theorem, let's consider this circuit and the terminals be A and B. Then according to Thevenin's theorem, across these terminals, this whole network can be replaced by a voltage source and a resistor in series with the load. So this is RTH, this is VTH, and this is 13 ohm, that is this resistance. Now let's understand how we have to find VTH and RTH. To find VTH, we have to remove the load from the terminals and find open circuit voltage across the terminals. So this circuit will be like this. So this voltage will be Thevenin's voltage, and it is very easy to find using KVL and KCL. You can find voltage across this, and as this is open, so there will be no current in this resistor. So this voltage drop will be equal to this voltage drop across this resistor, and you can either use KVL and KCL or you can use mesh analysis. If you don't know mesh analysis, then you can check my video. In this I am directly doing that. Let this be I1 and let this be I2. Then this will be equal to 10 plus 10, that is 20, minus 10 minus 10. This will be equal to 25. I1 I2 equal to 8 0. So we need I2. Using Cramer's rule, we can find I2 by replacing column 2 with this and finding determinant. This is like this, and dividing by the determinant of this matrix. So this comes out to be 80 upon 500 minus 100 equal to 80 by 500, 1 by 5 ampere. So VTH will be equal to 10 into 1 by 5, because VTH will be equal to potential difference across this resistor. This will be equal to 2 volt. Now we have to find RTH. That is Thevenin's resistance across the terminals A and B. And the method to do that is we need to eliminate all independent voltage and current sources. And to eliminate voltage and current sources, we need to replace them with their internal impedances. And ideally, internal impedance of a voltage source is 0. Internal impedance of a voltage source is 0, and internal impedance of a current source is infinite. So in other words, we can say that we need to replace voltage source with a conducting wire, or you can say we need to short circuit the voltage source and open circuit current source. So short circuit voltage source and open circuit current source. In this circuit there is only one voltage source, so after eliminating that, the circuit will be like this. You can see here that I have replaced the voltage source with zero impedance, that is with a conducting wire, that is I have short circuited the voltage source. Now finding the resistance across terminal A and B is very simple, and this will be equal to 10 is in parallel with 10, so this will be 5 in series with 5, so this is again in parallel with 10 and in series with 2, so this will be equal to 5 plus 2 equal to 7. So in this case RTH is coming out to be 7 ohm. So the Thevenin's equivalent network will be VTH, a resistor in series RTH, that is equal to 7 ohm. VTH was 2 volt and the actual load is connected in the AND. Now you can find this current. This current is equal to 2 upon 7 plus 13, that is 20, equal to 1 by 10 ampere. So this is how you convert a given network into its Thevenin's equivalent, and this circuit was quite easy and it was a DC network. For AC network we can state this theorem as across a pair of terminals, any linear network containing active and passive elements can be replaced by an equivalent network containing a voltage source VTH known as Thevenin's voltage and a series impedance ZTH known as Thevenin's. For AC, you need to just replace this term with impedance and this term with ZTH, nothing else. Rest of the analysis is same. As far as its significance is concerned, you might be thinking, why haven't we solved this network simply using KVL and KCL? And there is a reason. Thevenin's theorem provides us a way to solve complex circuits, and this is basically used when we are interested in a particular branch and not in other branches. For example, in this example, I was interested in current only in the 13 ohm branch and I was not interested what is the current in other branches. So Thevenin's theorem acts as a rescuer in such type of problems. And a very common example which you must have done in your 12th standard, in which you are supposed to find current in this branch. So in your 12th standard, what you have done, that you suppose this current to be I and this current to be I1, then you say that by KCL this current would be I minus I1, and let's suppose this current to be I2, then this current will be equal to I minus I1 minus I2, and this current will be equal to I1 plus I2, and this current will be again equal to I. Now what you did, you applied KVL in 3 loops. From there you get 3 equations, and as there are 3 variables, after solving them you can find this current. But same problem can be done by Thevenin's theorem, and much easily we can do this. And the reason is we are only interested in this branch, that is 3 ohm branch. And for example, let's solve this problem too with Thevenin's theorem. First, we will find VTH by open circuiting this branch. This resistance is 10 ohm, this is 20 ohm, this is 5 ohm, and this is 8 ohm. This current let be I1 and let this current be I2. So I1 will be equal to, this is 5 volts, will be equal to 5 upon 13, and I2 will be equal to 5 upon 30. So if this terminal is A and this terminal is B, then VA is equal to 5 minus 5 multiplied by I1, that is this. This comes out to be 40 by 13 volt, and VB will be equal to 5 minus 10 into I2, this current, and this is 5 upon 30, and this will be equal to 10 by 3 volt. So you can see that VB is at higher potential, so we can write VBA equal to 10 by 3 minus 40 by 13, and this must be equal to 10 by, and this is VTH. Now after finding VTH, we will find RTH, and for this we short circuit the voltage source. So this will be like this is 5, this is 8, this is 10, and this is 20. So as these two terminals are connected by a conducting wire, so these points will be at same potential, and we are supposed to find resistance across A and B. So you can see that these two resistors are in parallel, and then they are in series with these two resistances. This is 5, this is 8, this is 10, and this is 20. So RTH is 5 into 8 upon 13 plus 10 into 20 upon 30, and this comes out to be 40 by 13 plus 20 by 3 equal to, you can find using calculator, this comes out to be 380 by 39. So this whole network has been converted into its Thevenin's equivalent network containing a voltage source and a resistor in series, and now we connect the actual resistance across which we were interested in finding current, that is 3 ohm. This is RTH equal to 380 by 39, and VTH is 10 by 39. From here you can find I equal to 10 by 39 upon 380 by 39 plus 3 ohm, and this comes out to 10 upon 497 ampere. So, and the direction of current will be in this direction because VB is at higher potential. So this is how we find current in any particular branch by using Thevenin's theorem. I hope its significance is clear to you because of this example. That's all in this video. Thank you.